Hello everyone, today we're going to be doing definite integrals. So recall that one method of determining the area under a curve f of x from a to b is to use the following limit. This limit is also very useful in determining other quantities such as volumes, lengths of curves, areas of surfaces, and physical quantities such as work and force. This is the definite integral. So if we let f be a continuous function defined on the interval from a to b, the definite integral of f from a to b is this. So this highlighted notation is a lot more compact and a lot less writing. We're hopefully not going to dwell on this too much longer. So this symbol is called the integral. In this notation, f of x is called the integrand, a is called the lower limit of integration, and b is called the upper limit of integration. This symbol should be regarded as a single symbol. None of the pieces can be taken away, and the significance of dx will be explained later. The process of calculating an integral is called integration. For special cases where the function is above the x-axis, this is equal to the area under the curve of f of x from a to b. So in this question we're going to use the definition of the definite integral to evaluate this definite integral. Now if doing this question with sums makes you feel like making the following noise, you are correct. So we're just going to scroll right through this and do it the easy way instead. So before we go any further, we're just going to take a quick peek at the function, what it looks like, and that's going to inform how we approach this question in part A using definite integrals. So we're going to split this definite integral up into two intervals. We're going to go from 0 to 3, and we're going to go from 3 to 5, because this portion is above the x-axis, and this portion is below the x-axis. So now we put the function in, 3x minus x squared dx, and the same thing here, 3x minus x squared dx. So the question we asked ourselves last unit, where did this derivative come from, still applies with this notation. So this derivative would have come from the following expression, 3/2 x squared minus 1/3 x cubed plus c. And because we're doing a definite integral, we should indicate that. And we do the same for the other interval. This derivative came from the exact same expression. So 3/2 x squared minus 1/3 x cubed plus c. And this is on the interval from 3 to 5. Next we're going to plug the 3 in everywhere we see an x. So we'll go 3/2 3 squared minus 1/3 times 3 cubed plus c. And we would subtract 3/2, 0 this time, squared, minus 1/3 times 0 cubed plus c. And we need to add this bit as well. So we will go plus 3/2 5 squared minus 1/3 5 cubed plus c, and we would subtract 3/2 3 squared minus 1/3 3 cubed plus c. Now it looks like at this point this thing and this thing would cancel, but I'm going to leave these intact because this bit on the top line is the stuff above the x-axis, and this stuff on the bottom line is the stuff below the x-axis. So next we can simplify this. The c's would go away. This expression would be 0, that would be 0. So we just need to evaluate this stuff, and that works out to be 9/2. And we do the same for this portion. The c's go away, and we are left with negative 26 over 3. So this would be the stuff above the x-axis, and this would be the stuff below the x-axis. And if we add all this together, we get a result of negative 25 over 6, which is consistent with our earlier result using sums. So we've done part B here. You can see that. This would be a positive area. This would turn out to be a negative area. We did part C and found it to be 9/2, and we also did part D and found it to be 26/3. So the way these answers relate to each other, the area above was calculated in C, that was 9/2. The area below was 26/3, and the total area worked out to be the area above minus the area below, which worked out to be negative 25 over 6. So in general, if a function f takes on both positive and negative values, then we can interpret this as a difference of areas, given by this expression. So I'm going to leave example number 2 for you to do. I will leave it for you to prove that this is 15 over 4. I would recommend you try making a picture in Desmos. My new sponsor, just kidding, still searching. You can copy and paste what you need from this thing I made earlier today. All the elements you need are there. You can turn these elements on and off, as you can see. If we open this folder up, we can click these colored circles on and off, which you may not be able to see, but they're over there. You basically just need to switch the function and the limits of integration. You also don't need to multiply the integral by 100, as I've done here, but you can probably tell that from the note. Anyway, poke around a little bit, try this out. There's a link in the description. So that's it for me for today. You can try these questions out in the textbook as well if you like, and I'll see you next time.